Today we're going to be starting with Cambridge O-Levels Chemistry, Paper 4, Alternative to Practical, May June 2025, and Paper 41. So let's get going. A student determines the solubility of solid ammonium chloride in water at 60 degrees Celsius. He puts 100 cm cube of water into a beaker. He basically then heats the water, measures the mass of the weighing bottle containing aluminum ammonium chloride. Okay, so in order to understand these steps while you're performing an ATP paper, it's best to visualize what's happening. So firstly, he's putting 100 cm cube of water into a beaker. So he has a beaker and he puts 100 cm cube of water into it, and then he heats the water. So now there's going to be a heat source below and he's going to heat the water. When he's going to heat the water, you know that the temperature of the water is going to increase. Let's see what happens further. Measures the mass. Okay, now until now he has not added any ammonium chloride, but now he measures the mass of the weighing bottle containing ammonium chloride. Okay, so with the bottle he's measuring the mass of ammonium chloride. Adds some of its ammonium chloride to the water, not all, some of the ammonium chloride. Now this is the ammonium chloride that is being added to this water. Stirs the mixture to dissolve the solid. What's going to happen is that this solid is going to move into the mixture, and now as he stirs it, this solid is going to be dissolved. So now repeat step 4-5 until a small amount of dissolved solid remains in the beaker. Okay, so now what he's doing something clever that you might not understand. That he's not dissolving all the solid, all the ammonium chloride. He's not dissolving this ammonium chloride, he's just stirring it that it dissolves. But what he's doing, that he keeps on adding more and more ammonium chloride until there's a small amount of ammonium chloride that's going to be left in the beaker undissolved. So not all is going to dissolve, some is going to be left at the bottom that's going to be undissolved, but it's going to be a small amount. Okay, stirs the mixture to dissolve the solid. Repeats. Okay, measures the mass of the weighing bottle and unused ammonium chloride. So now again he's measuring that how much basically he has used, because by subtracting the mass of the weighing bottle containing ammonium chloride and the mass of the weighing bottle and unused ammonium chloride, he's going to get the mass of the used ammonium chloride. That's simple maths. Calculates the mass of ammonium chloride added to water. State one extra measurement that the student must make to calculate the solubility. Uh, Look, what he's doing is that he's simply adding water. He's adding some mass to the water. He has measured the volume of the water. He has measured the mass. But there is one extra measurement that the student must make to calculate the solubility, and that extra thing should be, imagine it yourself, something that affects the solubility, something that affects it, that's going to be temperature, because temperature affects solubility. Anything that affects solubility should be kept into account. So this extra thing that he should measure should be the temperature of what? Temperature of the 100 cm cube of water. So now the students' results are shown in table 1.1, initial mass in step 3. This is the initial mass, final mass in step 7. Okay, so now what kind of mass is 173.7? That's basically the mass of the weighing bottle containing ammonium chloride. So basically this is the mass of your bottle, something like this. Sorry for the bad drawing. I genuinely apologize if the drawing is not good. This is the bottle. This is the mass of ammonium chloride. Initially, there was a lot of ammonium chloride, but as you dropped your ammonium chloride, what's going to happen that in this step, the mass of the ammonium chloride inside the bottle, it's going to decrease. So now you have lesser amount of ammonium chloride left because you have added some of it to the beaker of water. Use the results to calculate the solubility of ammonium chloride at 60 degrees Celsius in gram per dm cube. Okay, so now how many grams of it dissolved in 1 dm cube, gram per dm cube? Okay, so first we have to find out the mass of ammonium chloride. If we subtract this mass from this mass, okay, the mass of this thing from the mass of this thing, we're going to get the mass that's basically used. Do you get it? The mass of ammonium chloride, if you subtract this from this, you're going to get this part That's basically dissolving in water. So it needs to be 173.7 minus 115.5. 173.7 minus 115.5, and that gives me 58.2 grams. Okay, so that's the mass that's dissolving, and I have to find out per dm cube that how much water I had. I need to divide it by the volume of my water. I had 100 cm cube of water, so 100 cm cube, I need to convert it into dm cube. I'm going to divide it by 1000 and I'm going to get 0.1 dm cube. So this mass of my ammonium chloride dissolved in this much of water. So now what I'm going to do, I need to find the mass that dissolved in 1 dm cube. So it's going to be 58.2 grams per dm cube, 0.1. 58.2 divided by 0.1, and that gives me 582 grams per dm cube. Explain why the method the student uses gives higher value of the solubility than the true value. Okay, so now when a question like this occurs that asks you something that's wrong happening with your experiment, that why the value is higher or why the value is lower, you got to read this part again and again. So over here we see that there is some kind of problem happening. He was trying to measure the amount of solubility of the salt in water. But what is the student doing? He's always taking some extra mass of ammonium chloride. How is he taking? Because he stirs the mixture to dissolve the solid, repeats step 4-5 until, this part is very important, that there's something wrong he's doing, until a small amount of undissolved solid remains in the beaker. So he's also measuring the mass of the undissolved solid. So this mass is also being measured. This mass should not be measured because this mass is not being dissolved. But why is he doing it? He's doing it to ensure that the maximum solubility of ammonium chloride is reached. Okay? That's why he's doing it. And that's an important step, but that's creating an error in the solubility. This extra mass is also being measured. So we have to tell the examiner that mass of the undissolved ammonium chloride is also measured. Because what he's doing, he's not removing it. What he should typically do is filter this out. Undissolved ammonium chloride is also being measured. So while reading these experiments, you have to be careful to find out anything that you find, that you think that this is an error. By reading it, try to figure out the errors. Okay? The student repeats the experiment at different temperatures. The results are shown. Okay, so now he's varying the temperature, he's increasing the temperature, solubility is also increasing with temperature. Estimate the solubility of ammonium chloride at 20 degrees. Okay, so now in estimation questions, you have to be very careful. Why? Because this is the table that you're given with, and now you have to create something of your own. Okay? Something of your own in ways that you have to look at the small details. Over here, from 0 to 40, when you increase the temperature by 40 degrees Celsius, the solubility increases by 180, right? 180. Over here, when you increase the temperature of further 40, the solubility again increases by 660 minus 480. Let's check. 660 minus 480 again by 180. So over here it again increases by 180. So you see that there's a linear increase between solubility and temperature. As the temperature increases, the solubility increases linearly. There's a direct relation. So even if they ask you to plot a graph of solubility and temperature, the graph of your solubility and temperature, degrees Celsius, gram per dm cube, it would be a straight line. But it will not pass through origin. Why not? I know I'm teaching some physics over here. It will be a little above origin, not like this. At 0 temperature, the solubility has to be 300, something like this. That's going to be a graph for it. How do I know it? Because I know that there's a direct relation. Increasing this value increases that value as well. Okay, so now I need to figure out at 20. I simply need to, 180 is the difference. I need to half this difference because I'm halving this. I told you there's a direct relation. So if I half 40, I get 20. So I need to half the difference as well. So 180 divided by 2, 180 divided by 2, that's 90. So from 300 to 20, there's going to be an increase in of 90. So I simply tell the examiner that what I'm doing is, because it's a 1 mark, I'm simply dividing 180 by 2. I get my answer as 90, and then I add 90 into my 300 to get 390. I hope you get what I am doing. Okay? The student wants to measure the solubility of ammonia. Suggest why the method used for ammonium chloride is not suitable for determining the solubility of ammonia. The method that we used, in that we had a solid. Okay? The method that we used, we were dealing with solids. But ammonia is a gas. Gas and solids. What's the difference? For solids, what we were doing, we were measuring gram per dm cube. We were measuring solubility in grams per dm cube. We were measuring the mass by putting it on a weighing scale. But for a gas, we cannot put the gas on weighing scale, right? So, difficult to measure the mass of a gas on a weighing scale. So we're gonna tell that difficult to measure the mass of the gas. On a balance or whatever. So that's why it's going to be difficult. Or agar we have to find, there's going to be, obviously we have to make the maximum ammonia dissolve, so there's going to be some undissolved ammonia left at the end, which we're not be able to figure out because it's an invisible gas, right? So we won't be able to see it. Okay, solid A is impure calcium carbonate. Okay, good information. It's impure, and secondly, it's calcium carbonate. A student determines the number of moles of calcium carbonate in a sample of A. Okay, the student places a sample of A into a beaker. Okay, what he's doing, let's try to annotate what he's trying to do. He has this only sample A, which is calcium carbonate. Using a measuring cylinder, adds 100 cm cube of 0.250 mole of HCl into the beaker. So now he's adding acid into calcium carbonate, stirs the mixture until no further effervescence is seen, labels the mixture B, calculate the number of moles of HCl used in the beaker. So for this, you simply don't need to do anything. You have the volume, you have the concentration. So you simply know that moles equals to your concentration times your volume. And your concentration comes out to be 0.250 times your volume, which is 100 cm cube, but you divide it by 1000 since you need to take it in dm cube. So 0.250 multiplied by 0.1, and that gives me 0.025 moles. 0.025 moles. Now there's a trick part. I know that since I know the moles of my HCl that's being used, I can also calculate the moles of my calcium carbonate. How? By a balanced equation. But let's see what the examiner asks. Okay, the student rinses a burette with water, then with 0.1 mole dm cube of sodium hydroxide. Okay, a lot to catch up. The burette is being rinsed with water, then with this concentration of NaOH, fills the burette with this NaOH. Okay, adds 25 cm cube of B. What is B? Labels the mixture B. So B has these many moles of HCl, but these many moles of HCl, out of these many moles, some moles of HCl would have reacted and some would have left unreacted. Okay? That's what I think. So you have to keep everything in mind. And put 5 drops of methyl orange indicator into a conical flask. Okay? What's going to be the color of methyl orange in the conical flask? We have acid in the conical flask, so it's going to turn red. Okay, so this in the conical flask, this methyl orange indicator, since I've acid in it, as far as I think, so it's gonna turn red. But let's see. Adds NaOH from the burette to the conical flask until, oh, you know what's gonna happen? I just got it now. The examiner is gonna make us calculate the moles of HCl in the, oh my god, this is such an interesting question. He's gonna make us calculate the moles of HCl that we're gonna use to neutralize this NaOH, and that means that out of the total moles, those many moles, they were not used, right, to basically neutralize this calcium carbonate. And then we're going to subtract the moles of HCl we find over here from this value to get the moles of HCl that basically reacted with calcium carbonate. And from those moles, we're going to figure out the moles of calcium carbonate. Oh my god, I just understood what the examiner is trying to do, and it's interesting. So let's get going. If you don't understand what I just said, it's fine. Okay? Still, just do simple steps, you're going to get it. He's going to guide us through. 2, 2.1, 2.2, 2.3, 2.4 is my initial volume. Burette reading 2.4 and final burette reading is 17.5, 6, 7, 8, 9, 10, 11. So that's 18, right? 18.1, 2, 3, a second. Okay, this is 18, right? Okay, so this one right here is 18. So this is 18.1. Final burette reading is 18.1, and 18.1 minus 2.4. What just happened to my calculator? Okay, 18.1 minus 2.4, and I get 15.7. So 15.7 here. 15.4 minus 0.2, 15.2 over here, and 30.8 minus 15.4. 13.8 minus 15.4. 30.8, sorry. 30.8 minus 15.4. Now I need to check my concordant results. Concordant results are those that have a minimum difference of 0.2 cm cube. Okay, those are concordant results. 15.7 and 15.4. The difference is 0.3 dm cube. Cm cube. So these are not concordant. The two best burette readings are gonna be this and this, because these two have a difference of 0.2 cm cube. Okay, take the best titration results, calculate the average volume. Now you have to calculate the average of 15.2 and 15.4. So we add them, divide them by 2, and we're gonna get 15.3 cm cube. Now the acid used in A to prepare the mixture of B is in excess. Okay, I got it before. Everyone should get it before. If you know chemistry, that over here, to prepare B, the acid was to be in excess. Why? Because when we made B, what happened? We had some acid left in it that we used to later on neutralize this NaOH. Okay? So what's happening is, if I summarize whatever is happening over here, if you don't get it, what's happening is that you have a beaker. Okay? You add acid to it. Okay? You add some calcium carbonate in it. The acid is in excess. So you add excess HCl. Now this calcium carbonate is gonna react, but there is still some HCl left over here. So now what do? You add some labels mixture B. Okay, so now there's still some HCl left in it. This is HCl. You label this mixture B. This mixture B has some HCl left in it. So now what do? You titrate this mixture B that has some HCl left in it with NaOH, and that's the titration happening. Okay? In simple words, I try to explain it. Use your answer to B2. Okay? Use your answer to B2 to calculate the number of moles of 0.100 dm cube NaOH that reacted with 25 cm cube of B. Okay, so now we had NaOH and the burette. So now we need to calculate the moles of NaOH, okay? Moles of NaOH. You need to realize one thing, that HCl के moles ratio NaOH के moles are going to be 1:1. Why 1:1? Because if you make a balanced equation, 1 mole of HCl is going to react with 1 mole of NaOH. And now use your answer to B2. This answer, that's the volume of NaOH, okay? This is the volume of NaOH, okay? Volume of NaOH. To calculate the number of moles of NaOH that react with 25 cm3 of B, we have the volume of NaOH, we have the concentration of NaOH. We need to multiply these two to get the moles, okay? We're going to use this ratio. Probably we have to use this ratio in the next questions or wherever, but I think we're going to use it. So simply moles equals to my concentration, which is this, times my volume, which is 15.3, but it's going to be divided by 1,000. So 15.3 divided by 1000 multiplied by 0.1, 0.00135, 0.00153, right? 153. Done. Number of moles. This is the moles of NaOH. Calculate the number of moles of NaOH that reacted with 100 cm3 of B. Okay, so that's the number of moles that reacted with 25. So if with 25, 0.00153 moles of NaOH reacted, then with 100, they're going to be X moles of NaOH reacting. So simply you use the ratio method. It's going to be 100 multiplied by 0.00153 divided by 25. I hope you get it. Multiplied by 100 divided by 25. We get 0.00612. 0.00612 moles. Okay. The answer to D is equal to the number of moles of HCl that remain in the beaker after the acid reacts with calcium carbonate in sample A. So these are the moles that are unreacted out of these many moles of HCl. Do you get it? So how many then reacted? This is the total number of moles of HCl, and this is the unreacted moles. So how many moles of HCl reacted then? Calculate the number of moles HCl that reacted. It's going to be this above value, which was 0.025. Okay, 0.025 minus this unreacted moles, which was 0.00612. Okay, minus 0.025, we're going to get an answer in minus 0.01 888. 0.01 888. Okay. You can write this to two significant figures or 3, but I have just written it to maximum because I want it. Okay. Now they've given you the ratio. Okay. So what's gonna happen is that calculate the number of moles of calcium carbonate. You know that HCl ratio calcium carbonate is 2:1. So if you have these many moles of HCl that reacted, 0.01 888, they're gonna be X moles of calcium carbonate. And how do you calculate the value of X? It's simply gonna be 0.001 888 divided by 2. So it gives me 0.00944. 0.00944. 00944. Okay, done and dusted. In A, the mixture of A and the acid is stirred until effervescence stops. Give a reason for mixing the reactants by stirring. So, are you stirring? So, there is basically even mixing so that nothing undissolved remains That's why we are mixing the reactants by stirring. Nothing remains undissolved. Simple. I don't think you need to use any logic over here. Just write that nothing remains undissolved. Okay, so that there is an even mixing of reactants, even mixing of reactants, or you can say there is a uniform mixing of reactants. That's all. Give a reason for waiting until the effervescence stops. So simply that the reaction is over. To wait for the reaction to be over. Okay? To wait for reaction to stop. Reaction to stop to make sure all calcium carbonate has reacted. To make sure all calcium carbonate has reacted. That's all we want. In A, the measuring cylinder is used to add 100 cm cube of this to the beaker. Explain why the measuring cylinder makes the volume of HCl used inaccurate. Suggest an improvement. Measuring cylinder has a less precision. So simply gonna tell less precision or large percentage uncertainty. Large percentage uncertainty in value that's gonna be obtained from the measuring cylinder. Measuring cylinder, I'm writing like this. Okay, improvement is gonna be you can use a burette because burette is more accurate, or a pipette. So these are gonna be more accurate. In B, the burette is rinsed with water and then with this mole of NaOH. Explain why the burette is rinsed with sodium hydroxide after rinsing it with water. So that the concentration of NaOH does not change. Because if you have a burette like this, okay, and you rinse it with water, so there are going to be some water droplets that are going to be left on the walls of the burette. And now if you add your sodium hydroxide, the sodium hydroxide is going to mix with this water and it's going to become dilute. Okay? So you don't want to change the concentration of sodium hydroxide. So the concentration, because water dilutes things, that's why you wash it again with sodium hydroxide. So there's no water on the walls. So concentration of NaOH remains unchanged and it is not diluted because you don't want any inaccuracy, and it is not diluted by the water that you're gonna that's gonna enter the system. Now question number 3 states a student tests two aqueous solution W and X. The student adds aqueous chlorine to W and concludes that W contains iodide ions. How can a student add chlorine to a solution and tell that it contains iodide ions? It's simple. It's very simple. And you're gonna add it to bromide ions. You're gonna take two bromide ions and then you're gonna form Br2 plus Cl2 negative. What's basically happening is electrons are being transferred from bromide to chlorine atoms, and because chlorine is a very strong oxidizing agent, that means it can attract electrons from literally anything, like not from just fluorine, but otherwise it can just attract from anything, not from fluorine and oxygen and nitrogen, I guess. Okay, otherwise from bromide iodide it can easily like just take away electrons. So what's basically happening over here, the student adds aqueous chlorine is being added to W and conclude that W contains iodide ions, because what he might have observed is that when he's adding that chlorine to iodine, let's take iodine for now, we just took bromide, two iodides, and then we're going to forming iodine. So what happens is that when he added this chloride to iodide ions, he must have formed iodine, and iodine's color is, you should know, if we form iodine in an aqueous solution, meaning in liquid form, so the color of iodine is gonna be, you think it's gonna be blue black? No, it's not gonna be blue black. Blue black iodine is like when it's a solid. or when you add starch to it. Otherwise, iodine in aqueous solution is a brown yellow kind of a liquid. Describe the observation the student makes leads to this conclusion. Observation and explanation. Observation is simply going to be that he observes a yellow orange orange liquid forms. ठीक है, a yellow orange liquid forms, or you can say solution turns yellow orange. ठीक है, and the explanation is simply what I told you, that chlorine is a strong oxidizing agent. Strong oxidizing agent, like it can just take away electrons from a lot of atoms. So it's a strong oxidizing agent, so it oxidized iodide ions. People say that for practical you don't need theory. If this is not theory, then what is this? You need to know the basic chemistry theory for the practical. Okay? If you don't know redox things, you're not going to be able to do it. Chlorine is a strong oxidizing agent, so it oxidized iodide ions to form iodine. Describe another test and the observation that confirms W contains iodine. What do you do to test for iodine? It might be written, it might not be written, but you know that you're going to add starch solution to it. You know that iodine and starch, what they're going to form? They're going to form a blue-black complex. And the observation is going to be blue-black solution turns blue-black. Okay? So, solution turns blue-black. The student does a flame test on W and observes a lilac flame. Lilac flame is for potassium. If you don't know, no worries, it's going to be given at the end. Describe how the student does a flame test on W. First, you need to realize if W is a solid or a liquid. A student tests two aqueous solutions of W. So W is an aqueous solution. So when you have an aqueous solution, what do? You take a wire, you basically dip it in W, and then what do? You put the wire on a blue roaring means that makes a roaring noise. That's going to be a blue Bunsen flame. I don't know if you guys have ever noticed, but in lab, if you have a dark blue roaring Bunsen burner flame, that's going to make a noise like soo kind of a noise. Okay? Put the wire on a blue roaring Bunsen burner flame. Okay? So that's going to be the test, and you might realize what these 2 marks for. The first mark is going to be that you're going to be dipping the wire, and the second part is going to be for that you have a blue roaring flame. Okay? If you don't tell blue, you just say flame, you're not going to get your mark, because on a normal flame the tests will be camouflaged, they won't be that good. You have to use this flame. Identify W. So W has lilac color, that means it's going to be having a potassium ion. Okay? That is what we know, that there's going to be potassium ion present. So K ion identified from this. And over here we just identified that it had an iodide ion. So it's going to be potassium iodide. Simple. You just have to write that this is potassium iodide. Okay, so now we have some more tests. X contains 1 anion, 1 cation, piece of cake, because we have a qualitative analysis table. We're going to be doing it in seconds. The student adds aqueous sodium hydroxide to X, warms the mixture, holds a piece of damp blue red litmus paper. What is this test for? What is the student testing for? Ammonium ion. Simple. Add sodium hydroxide, warm, that's going to be ammonium ion. Add sodium hydroxide, then aluminum foil, then warm, that's going to be nitrate ion. A white precipitate, soluble in excess, aqueous sodium hydroxide is formed. A white precipitate that's soluble in excess. Go to the table below, see white precipitate soluble in excess of, this is soluble in excess, then this is insoluble, so definitely not this, and white PPT soluble in excess. So either it's aluminum or it's zinc. And how do we confirm which ion is this? We are simply going to add aqueous ammonia, because in aqueous ammonia this aluminum thing is going to be insoluble, but zinc is going to be soluble. So moving back, Uh, State three conclusions that are made from these observations. The litmus paper does not change color. That means there is no ammonium ion. Okay. First conclusion is gonna be no ammonium ion. Okay. The second conclusion is gonna be that a white precipitate that's soluble in excess, it's gonna be either zinc 2 plus or either aluminum 3 plus. Getting it? So that is all I can deduce from this. Okay. Conclusions in D, identify the cations may be present. Okay, what do we do to check the cation? What do we do? We're just gonna add ammonia and observation. Describe another test that the student does and its observation to identify the cation in X. So the test is gonna be that you add aqueous ammonia, and the observations are gonna be that if it's gonna be, then adds a piece of aluminum. Okay, so if it's gonna be a soluble precipitate, it's gonna be zinc. If it's gonna be insoluble precipitate, it's gonna be aluminum. So we simply tell the examiner, you guys should write the entire thing. I'm just writing it to explain it to you guys. They write the entire thing, add aqueous ammonia and all that. Observations, if there's gonna be Zn 2 plus ion, you're gonna also add it in excess. So first add 2 drops and then add in excess. If Zn 2 plus, then you know the precipitates, they're gonna be soluble in excess. You just copy it down from below. And if you have your aluminum 3 plus ion, then the precipitates are going to be insoluble in excess. So you write precipitates insoluble in your excess of NH3. Okay, the student adds excess sodium hydroxide to X. Okay, he adds excess sodium hydroxide to X, then adds a piece of aluminum, foil and bombs. Ammonia gas is given off and tested with damp red litmus paper. Describe what happens to the litmus paper. You're testing ammonia gas, and what's the property of ammonia gas? Ammonia gas turns damp red litmus paper blue, so it's gonna turn blue. Identify the anion in X. This is a test for nitrate ion. Okay, this should be on your fingertips. Now we have a 6 marks question, for which I guess you should spare some time at the end, okay? So that you're able to think about it, because you have to plan it. Use a mixture of solid magnesium oxide and solid barium sulfate. Okay, so you know the properties of barium sulfate. What are the properties of barium sulfate? Barium sulfate is an insoluble salt. In magnesium oxide, it's also going to be insoluble. Magnesium oxide is insoluble in water. I told you it reacts with dilute HCl to make a solution of magnesium chloride. Barium sulfate is insoluble in water and does not react with dilute hydrochloric acid. I guess it's simple enough. What are you going to do? How are you going to separate them out? Simple, take barium sulfate, take magnesium oxide. Okay? What are you going to do? Add HCl. This magnesium oxide going to react, barium sulfate not going to react. So you simply filter out barium sulfate. Okay, and you add this acid in excess to make sure all the magnesium oxide has reacted. Plan an investigation to obtain pure magnesium chloride crystals. Okay, pure, and then what do? You just crystallize the filtrate and pure barium sulfate solid from Q. Your plan should describe the use of the, I just tell you what you do. Okay, over here, let's draw, annotate, and try to understand. You have this beaker. In this beaker, you have, this is your magnesium oxide, okay? And this green one is your barium sulfate. Now you add HCl to this beaker. This is HCl, okay? This is HCl. Now what happens is this magnesium oxide is going to react with this HCl, and the equation for the reaction is that your HCl plus magnesium oxide gonna give you MgCl2 plus, this is going to be salt formed and there's going to be water formed. Okay? Add it 2 over here. Done? Now what do? Now, simple as that, since this MgO will react. So now what is going to be left? Barium sulfate. That is not going to react. You just need to think in steps about this. This is a piece of cake if you're able to think. So magnesium oxide react, and if this react, now we have what kind of mixture? We have magnesium sulfate present in this mixture. Okay, so we have some magnesium sulfate, but that's soluble, that's not insoluble. The only thing that's insoluble is our barium sulfate. So now we filter this out. The next step is going to be filtration. How do we filter out? We have a filter funnel that is lined with the filter paper, and we have a beaker below. Now we basically pour this mixture. Our barium sulfate is going to appear at top, whereas our mixture of magnesium chloride is going to be at the bottom. Over here you need to make sure that you add HCl in excess. Why do you add HCl in excess? To make sure that all the magnesium oxide that was here has reacted. So now we know that our MgO has reacted, it's gone. Now our barium sulfate that we got from here, the barium sulfate that we got, what we're gonna do, we are gonna wash it, because this barium sulfate, it might be impure, there might be some problems with it, there might be some solution from which we filtered out. So what do? We wash it with water. We're gonna wash it because it's a precipitate, and then we're gonna dry it, and now we have pure barium sulfate. Next thing, what do? We have our this filtrate solution of MgCl2. Okay? So now to deal with this solution of MgCl2, we're gonna crystallize this. How do we crystallize? We basically pour it into a evaporating dish. So we pour it into a evaporating dish, and this solution in the evaporating dish, what are you gonna do? This is evaporating dish. We're gonna heat it till saturation point, or you can call it the crystallization point, saturation point, or crystallization point. And once you're gonna heat it, then you're gonna allow it to cool. What's gonna happen, that as this thing is gonna cool, there are gonna be some crystals formed in it, and those are gonna be MgCl2 crystals. Now you have the crystals. What do you do with crystals? You dry the crystals, and here you go with pure crystals. Over here, this was a simple procedure that you're gonna follow. I don't think there's something complicated. The apparatus, you can tell you're using beakers, you're using Bunsen burner, you're using an evaporating dish, you're using a filter funnel. Simple. And how do you dry? You dry between filter paper sheets. You can dry. Okay, that's all. Don't try to wash this crystal over here, because this crystal is basically, if you try to wash crystals, I think they're gonna wear off or something's gonna happen. So it's better if you just dry the crystals. But for precipitates over here, you're gonna wash them as well, because they're not pure, because they have some of the filtrate on them, because filtrate is gonna be poured over like this. So that's it for today's video. I hope you liked it. Do consider subscribing to the channel. That's gonna mean a lot.